So we're now covering lesson 2. We're still talking about work done, but this time we're going to be talking about specifically work that is done by a spring. So before we actually move into there, we're just going to review the work from yesterday. A child slides a toy towards a friend. It comes to a stop after moving 55 centimeters. The mass of the toy is 560 grams. Coefficient of friction between the surface and contact is 0.24. Calculate work done. All right, so let's write out our given. Okay, I don't know if you see this key term slide. That means I don't have an applied force. So it left my hand and it just keeps sliding. So the only forces that are acting on this object is actually force of friction. And it comes to a stop after moving 55 centimeters. So hopefully right away you recognize that when it says centimeters, we have to change it to the SI unit, which is meters. The mass of the toy, so M is 560 grams. Hold same thing. Hopefully you see that this is not the SI unit that you would want. So we'll have to divide it by 1,000. Go from the base to kilo. Coefficient of friction is mu. Mu is 0.24, not force of friction, right? They didn't give you FF. They gave you coefficient of friction. You need work done by friction. From yesterday's class, we talked about that if the force is opposite to the displacement is negative work done. So the equation for work done is negative FF times delta D. I have the D. I don't have the force of friction yet. That means I need to work it out. You actually need to go back to unit 1. So let's draw a free body diagram. I know that there is FG and FN always on the picture. It's sitting on the surface and there is force of friction that's acting this way. And if you remember the equation for force of friction from unit 1, it's mu Fn. And how do I calculate Fn? I need to study the y direction. Fn equals to your Fg. And all these things you need to remember. Do you remember how to calculate Fg? Fg is mass times 9.8. So I'm going to have to do like multiple steps to be able to find my force of friction. So m times g, the mass is 0.560 times the g, which is 9.8. So 0.56 times 9.8, 5.488 Newton. Okay, that is my force of normal. So now that I got my force of normal, I'm going to put it into this friction equation. So mu is 0.24 multiplied by the force of normal that we just found, 488. So I'm going to times it by 0.24. I have an answer for force of friction that equals to, all right, super big number, well, not big, but long number, 1.31712 newtons. Finally, putting it back into the work equation, negative 1.31712 times D. If you want to round it earlier, it's fine. I like to keep all my decimals and round it at the end. So my answer is a work that is a negative work done. And I'm just going to keep it into 2 significant digits. And if I ask you the same question, what's the unit for work? Say it. Do you know it? Joules, okay? So hopefully you remember. All right. This is called typical test question. You know you're getting this question on your test, okay? So make sure you remember the frictions and all those steps. Okay, so going back to the work equation that we've learned, just recall, work is force times displacement. And we assume the force to be constant. Now I need you to think about an elastic. When you stretch an elastic, to stretch it a certain distance, it's actually not proportional. Okay? What happened is the amount of work done, if I stretch the elastic at the beginning, it doesn't take as much force. But as it gets tighter and tighter and you stretch it more, it actually takes a lot more force if you want to stretch it for like the last half of the distance that got changed. Okay? And that makes it an issue with the equation. We actually cannot use this equation when we're finding work required to stretch a spring because it's actually not the force is not constant. And so we can't use it. So they tell you that you are going to use a different equation. to find the force first. Force is equals to K times delta X. Force depends on the amount of stretch, okay? And if I have a regular spring, okay, let's draw a spring here. That is at equilibrium, okay? What delta X is either if I push it and squish it all together, like making it tighter, the delta X is this. How much did I go from equilibrium? So this is called equilibrium, meaning it's not stretch or it's not push. If I push it by a certain distance, that is your delta X. Or opposite to that, instead of pushing it, you also could be stretching it. I'm going to change color. That's what I wanted to do. Okay, so from here, instead of pushing it, you can also stretch it out. Okay, and delta X could also be how much did you stretch it out. Okay, and then K is called the spring constant. Basically, K describes how stiff the spring or elastic is. If I have a really thick elastic versus a really thin, flimsy one, your K would be different. It's measured in Newton per meters, meaning for something that is really flimsy, this number would be small because it doesn't take a lot of force to stretch it a certain distance. But if it's like in car suspension, those springs are so tight, even to move it like a tiny half of a centimeter will take a lot of force, then you would have a large spring constant, which is K. All right, so we have force versus stretch graph. So if we do a graph like this, okay, kind of similar to when we were doing I don't know if you remember the displacement graph and stuff like that. And basically every time if they have a force versus spring graph, force versus delta X graph, and say for example, if they would like you to find work done, you find the area. If you wanted to find the spring constant, you find the slope of the line. So you have to read the question carefully. So that means you need to have this in your study notes, right? So you remember, if they give you a graph and they want the spring constant, you find the slope. You calculate the slope, okay? All right, question 1. What force is necessary to stretch a spring whose force constant is 120 Newton per meter by an amount of 30 centimeters? So they gave me force constant, which is K, 120 Newton per meters. And then they give you the stretch. The stretch is delta X. It is 30 centimeters. Okay, we don't like centimeters. We have to convert it into meters, so I have to divide it by 100. Oops. So it worked out to be 0.30 meters before I can put anything in the equation because we like everything in SI unit. Force is K delta X. So K is 120 Newton per meters. Newton per meters times delta X, which is 0.3. So 120 times 0.3 gives you 36. Unit for force is Newton. So like always, 3-mark question, 1 mark for equation, 1 mark for plugging it in, and 1 mark for the answers with the proper units. Question 2. A spring of a pongo stick is compressed 12 centimeters when a 40-kilogram boy stands on the stick. What is the force constant for that? Okay, this is slightly tricky. They added a twist. It compressed for 12 centimeters. That is your delta X. 40 kilogram, that is a mass. Okay, all right. Why are they giving me mass? I want to find the force constant, which is the K. The equation we know for the force constant is F equals K delta X. All right, I have the delta X, okay, which is good. I have a mass. What do you think the mass? What do I do with the mass? How do I put it in so that I can have an F so that I can solve for that? So the boy is standing on it. The 40 kilogram is standing on the stick. If you understand it, the force is actually the force of gravity acting on the stick by this boy. So it's actually M times G. So you need to work out what your force is first. So 40 times 9.8 is the force. So 392 Newton. You can't put 40 kilogram into an F. It's not the right unit, right? So that's why I've been stressing. If you know your unit, you know what to do with it. Okay, so I can't plug in my M into the F, right? But now I've turned it into a force of gravity that's pushing down on the stick. I have K, and the delta X is 12, which I forgot to convert. Hopefully you did, right? Make sure that you would turn it into meters by dividing it by 100. So 12. I wish I'm teaching in real life. I'm going to ask you how many of you actually remember that, all right? So make sure you convert that into SI unit. So 0.12. So to rearrange the equation, K is 392 divided by 0.12. Okay, it's equals to 326. I'm just going to round it to the whole number, 7 Newton per meter. That's a unit for K. I know I haven't been solving the math like that, but this is just rearranging the equation. This is multiply, so to bring this over, you would divide it on the other side. But one way that we have been doing is I'm just going to do it on the side because this is the way that I'm used to be teaching, depending on how comfortable you are with rearranging equation. If you're not, use your magic triangle. F is K times X. Times means they're beside each other. I've been teaching you how to build your magic triangle even if you're teachers or you don't have it. And then you cover up what you're looking for, which is your K. So K is what you're looking for. So F is at the top. Delta X is at the bottom. So it's F divided by X. So then it is 392 divided by delta X. See how it's the same thing, right? So either way, you should get the same answer, all right? Next question, using the graph, calculate work done with the spring for 0.24 meters. So the 0.24 meters is right there at the end. And if we would like work done, so part A, we're calculating for work done. And when I'm given a graph, hopefully you remember that you can go back to this or you have it on your study note. I have the graph. I want work done. I need to calculate the area under the graph, meaning I need to draw the block. This is the graph, is the black line right here. The area under the graph is going to be this triangle. So I'm going to say that it is going to equals to the area of a triangle. And I know a triangle is 1/2 base times height. So 1/2, the base, this is the base. So it's 0.24 meters. And the height is from 0 to 20 Newton. So 20 Newton. Okay, so 0.5 times 0.24 times 20. So I get 2.4 joules. Not going to ask you that. Maybe I should. Okay, so that's the first part. Part B, asking for what is the value for the spring constant. So go back to your sheets. I want spring constant, so I'm going to look for the slope. Okay, then I'm going to come back here and I'm going to look for the spring constant has a K and it equals to the slope. So I'm just going to write the slope. If you remember the slope of the line, we use the symbol M is y2 minus y1 over x2 minus x1. So pick 2 points from this black line. This is an easy one, a 0, 0. I always pick things that are on the grid that's easy. Okay, this other point is along the axis 0.24 and then the rise is 20. Okay, so the y2, so this is your x1. So from this is your 0.1 and this is your 0.2. So this is your x1, y1, and this is your x2, y2. So from the equation, y2 is 20. Subtracting y1, which is 0, divided by x2, which is 0.24, minus x1, which is 0. So 20 minus 0 is 20. 0.24 minus 0 is 0.24. So 83.3 Newton per meters. All right.